In this video, we'll be discussing the basics of parallel termination. I'd like to make future videos on other types of termination, such as series, Thevenin, and so on, but for now we'll focus on a very simple and very effective method, which is parallel termination. The boards you're seeing here are fairly high-speed digital boards, and oftentimes when we get into these high-speed digital areas, we need to think of termination, as we'll see, to minimize reflections, improve signal integrity, and EMI performance. I'll show you how I did this on some of these boards. For example, on the bottom left board, this ZBed, we have some DDR memory, and on the bottom side, if we zoom in a bit, we can see this array of resistors, which are in fact parallel termination resistors. On the right-hand side, we can see this for this other PCB. Around the DDR3 memory, we have this array of termination resistors. The question is, when do we need them? Why do they work? How do we size them? How do we place them? And so on. And all of this I'd like to discuss in this video. A huge thank you to Altium for sponsoring this video. Make sure to check out the link in the description below, or go to altium.com/YT/PhilsLab, and you can get yourself an Altium Designer free trial, as well as 25% off your first license purchase, and you can check out all the cool features, including Altium 365. Please visit the link in the description below to learn more about Altium 365 and many of the cool features, such as ECAD, MCAD integration, library management, design reviews and markups, and much, much more. Octopart is also a part of the Altium ecosystem, so make sure to go to octopart.com, which allows you to search for millions of components across hundreds of component distributors very easily. A huge thank you to PCBWay for sponsoring this video. The boards you just saw at the start of this video were manufactured and assembled by PCBWay in China. These are fairly complicated boards with very narrow features, such as 100 micrometers, high layer count boards with controlled impedance, and they did an absolutely fantastic job, and I'd highly recommend you try out their services. For those particular boards, I went with their advanced PCB service. At the time of making this video, the PCBWay project design contest is also live up to January 2024, and I'd strongly suggest participating with your own designs. There are various prizes available, and further details can be found in the link in the description below. Before we start looking at parallel termination, let's go over what termination is and why we need it. Termination exists in various different signaling, for example RF and digital. In this video, I will be focusing on high-speed digital logic. High-speed digital logic I've put here in quotes because high-speed is a very hand-wavy term. Effectively, high-speed typically means short rise and fall times, so fast edge rates, and comparatively long transmission lines. If you'd like more detail on how to calculate when something is, for example, high-speed, make sure to check out video number 64 on my channel. In any case, assuming we have short rise and fall times and we have fairly long traces, then we need to be concerned with topics such as controlling impedances and also termination. Let's look at the top right image. Assuming we have a digital logic driver, which has a certain output impedance ZS, let's call this the source impedance, this sends a fairly high-speed digital signal, so fast edge rates, along a trace, which in this case will then be a transmission line of length L. This transmission line will have its own characteristic impedance. At the receiving end, we have our load, which also has its own impedance, ZL, the load impedance. At any of these interfaces, very simply speaking, and this is a very simplified view, so any boundary between where we have different impedances, so ZS to ZTL or ZTL to ZL, any mismatches in those impedances, so if ZS isn't equal to ZTL or ZTL isn't equal to ZL, these mismatches between the driver, the transmission line, and the load impedances will result in reflections. Reflections are something we want to minimize, as reflections are pretty bad for our signal, as they lead to overshoot and undershoot, and quite severe overshoot and undershoot if the reflections are very large. This could be volts of overshoot and undershoot in certain cases. This then leads to signal integrity problems. We might exceed maximum ratings of the input ratings, we might exceed logic margins if we have too much undershoot, and generally our signals will be very distorted. In addition, reflections and improper matching of impedances can also impact the EMI performance of our system, which means ringing, increased frequency content, and so forth. On the bottom right-hand side, I've taken this from a Texas Instruments application note. This is looking at an RS485 transceiver system across a fairly long distance. On the left-hand side, we can see waveforms without termination. We can see for a given input signal, the output transceivers waveforms are very, very distorted with overshoot, undershoot, additional frequency content, and so on. Once we've added in termination, this is what our waveform then should look like at the bottom right, far, far cleaner waveforms. So the image on the left-hand side, where these reflections come into play, that's what we want to try and avoid. One way of doing this is, other than controlling impedance of our transmission lines, is then also to look at termination. And this is what we're going to be starting to look at in this video. Termination therefore aims to reduce the magnitude of these reflections, and this is done by impedance matching. So if, for example, our transmission line impedance isn't matched to our load impedance, we can add in termination to make sure there's a better match to reduce the reflections, and that's what termination is all about. This in turn then, with our reduced reflections, means improved signal integrity, EMI performance, which in turn leads to higher possible data rates, longer possible line runs, and so forth. There are, of course, many types of termination possible, and this is entirely dependent on the situation. Different termination schemes have different pros and cons. You might have heard of series termination, effectively just a resistor placed in series at the driver output, parallel termination, which we're looking at in this video, and then there's also AC parallel, Thevenin diode, and so forth. Before we can look at parallel termination, we need to look at reflections in a bit more detail first. For this, I've changed the diagram a tiny bit, but now we'll look at the driver having the same impedance as the transmission line, so both Z0, which we'll call the characteristic impedance. So we assume the driver is matched to the transmission line impedance, so we get no reflections at this driver transmission line boundary. However, we do have a load at the end of the system which acts as our receiver, and let's say we can vary the load impedance. Then we'd like to see what happens at this boundary where the transmission line effectively meets the load, where we have this impedance discontinuity. The reflection equation, this is something you might have seen before, in percent is the load impedance minus the source impedance effectively divided by the sum of the two times 100%. These reflections then occur at impedance discontinuity. Let's go over to a graphing calculator and plot this equation. I've plotted the equation here, so on the x-axis we have the load impedance, on the y-axis we have the reflection in percent, so going from minus 100% to plus 100%. I've just set a characteristic impedance fairly typically at 50 ohms, so this will be our, for example, transmission line impedance. Immediately we can see when we get no reflections, so when we're crossing the x-axis, we can see that the load impedance needs to match the source impedance, or in this case, the characteristic impedance. So when ZL equals 50 ohms, we cross the x-axis and we get 0 reflections, which is the ideal case. If our load impedance, so ZL, is greater than Z0, we start getting positive going reflections. These will add to the incoming waveform, to the incoming voltage. So above 50 ohms in this case, we start getting more and more positive going reflections, and of course our limiting value for very, very high load impedances is 100% reflections. On the other side, however, if our load impedance is less than 50 ohms in this case, so less than the characteristic impedance or the source impedance, we will get negative polarity reflections. So these will subtract effectively from the incident wave, all the way down to minus 100% negative going reflections. We can of course vary the characteristic or source impedance, so if I go to, for example, 40 ohms, we can see we have a match if our load impedance is also 40 ohms. And the curve characteristics are very similar, except our zero crossing point is wherever our characteristic impedance or our source impedance is. To summarize then, if ZL equals Z0, then we have a perfect match and we have no reflections. And this is the ideal case, and this is what we're striving towards. If the load impedance is larger, we get positive going reflections, so the reflection adds to the incident wave, and this means we get overshoot, and this isn't a great thing. In general, you'll also probably know that the load impedance is typically far, far higher than transmission line or driver impedance. For example, the load impedance might be several kilo ohms, whereas the driver impedance on transmission line impedance will be maybe tens of ohms. Therefore, typically without termination, we can usually expect positive going reflections, because we have a far larger load impedance than the driver and transmission line impedance. This is a pretty big generalization though. On the other hand, as we saw, if the load impedance is lower than the transmission line impedance in this case, or ZL is less than Z0, we get negative going reflections, which leads to undershoot. Now, it used to be that overshoot was the culprit and something we wanted to avoid, but in modern digital logic, where we typically have in high-speed digital logic fairly low signaling levels, so maybe even just a volt, undershoot is more of a problem due to this small noise margin due to the lower logic levels. Comparatively, for overshoot, input voltage violations are less of a concern these days. So if we can choose between overshoot and undershoot, we do rather have overshoot, very, very simply speaking. Having looked at why we need termination, that is to minimize reflections, and what type of reflections we might expect, let's move over to looking at a specific method of termination known as parallel termination. As we saw before, typically the driver and line impedance is comparatively much smaller than the load or receiver impedance, meaning that, thinking back to our reflection equation, that we get large reflections at this transmission line load boundary, where we have this large impedance mismatch. One solution, again this is one of a few, is then effectively at this transmission line load boundary to have the line terminated at the load side by a parallel resistor of value RT. So this is our termination resistor. So we place this after the transmission line in parallel with the load, and we tie it to some sort of termination voltage, VT. Because RT is chosen very similarly in magnitude to the transmission line impedance, so far, far lower typically than, for example, the load impedance. As the parallel resistor RT is effectively in parallel with the load impedance, and RT is far smaller than ZL, the resistor dominates this parallel magnitude. Therefore, thinking back to the reflection equation, because the transmission line, very simply speaking, now just sees the termination resistor as a load, and the termination resistor is pretty much equal to the transmission line impedance, we severely minimize our reflections. The resistor effectively absorbs the additional energy, and this is a very, very simple and very, very effective termination method. With this termination method, we have to ask ourselves a few questions, and we'll look at some practical examples in just a second, and we will also do some simulations. The question is when we need this, what rise and fall times, transmission line lengths, and so on. Typical use cases might be in DDR memory, where we'll see this as DDR termination, in CAN systems, LVDS, and so on. I'll leave a few of these application notes in the description box below, and this gives you far more information on this topic, and I highly recommend looking through these various websites and application notes. What you might have also already noticed or suspected is that our driver needs to be fairly strong. This is because rather than now seeing a very high impedance load, this driver effectively just sees this termination resistor as a load. So for a 3.3 watt logic and a 50 ohm termination resistor, that's quite a considerable current draw for typical drivers. So you need to make sure your driver can handle this. Also, power consumption is of concern. Depending on what our termination voltage is tied to and what our driver output level is, so high or low, we will get varying DC currents through this termination resistor. Now, for a single line, you might not be too concerned with power consumption, but what about for a parallel bus, such as DDR memory, where you have many individual lines that each need their own termination resistor? This becomes quite considerable. Another question is, of course, then what the termination voltage needs to be. Is it VCC, so whatever the logic level high is, or is it ground, or is it some other voltage? For example, a VTT voltage for DDR memory. We might want to choose this VT, this termination voltage, to minimize the average power consumption. And this entirely depends on the bus you're dealing with or with the signaling you're dealing with, where you tie this voltage to. And we'll look at some DDR memory examples at the end of this video. What we also, of course, need to be concerned with is the magnitude of our termination resistor. And previously I said this should be around the transmission line impedance. And let me explain why it should be around that and give you more specifics now. Keep in mind that for realistic transmission lines, so when you go to your PCB manufacturer and you ask them to control the impedance of your tracks, they will give you a guaranteed tolerance of that impedance. This could be 5% in very good cases, but typically will be around 10% tolerance. So if you ask for a 50 ohm controlled impedance line, this could be 50 ohms, it could be 45 ohms, or it could be 55 ohms. Similarly, for the tolerance of the termination resistor, typical resistors might have a tolerance of 10%, but you might want to choose your termination resistor to have a better tolerance of 1%. The reason we care about tolerances is to remember that we have different types of reflections, positive going ones and negative going ones. What we want to avoid in high-speed digital logic, modern logic, is the chance of undershoot. So when the termination resistor is less than the characteristic impedance of the trace. Therefore, the general consensus is to choose the termination resistor higher than the transmission line to account for tolerances. So choose the termination resistor value approximately 10% higher than the transmission line impedance. And keep in mind, this is a rule of thumb, and you should do worst-case calculations to make sure you don't get undershoot. Some more ideas we need to be concerned with parallel termination are, for example, placement. Remember, we want to place parallel termination resistor at the load. But what does that even mean? I've put in 3 images here of examples of where we could put this termination resistor. So we have a line coming in from the left, then we have the termination resistor in parallel going into a receiver buffer. So this could be placed ideally on the line, just a short distance before the input of the buffer. So the left-hand side is a somewhat ideal case. The middle picture shows it could be a lumped distance after the load, so an electrically short distance after the load. So we go into the buffer, we route out of the buffer into our termination resistor. That's also valid. And lastly, we have a termination resistor placed with a short stub rather than directly on the line. Stubs are something we really have to worry about for very, very high-speed digital logic, as any stubs will decrease the signal integrity of our system. So if you can, placement as in the first picture or the middle picture. Again, lumped distance to the load. We can also, of course, have parallel termination for bidirectional lines. This is when we'll need a termination resistor at each transceiver. We also have parallel termination for differential signaling, and it's the same principle. Effectively, our termination resistor spans across the differential pair. Where we have the termination resistor value is the differential line impedance, nominally. Of course, there are many different termination schemes also for differential signaling, but we'll leave it at this for this video. Let's go over and do some simulations and look at how this is implemented on real-world systems. Now let's go to Altium Designer and look at the signal integrity tool to do some very basic simulations, looking at the reflection waveforms with and without termination, and then also look at how we would place these termination resistors and choose them in real-world situations. First of all, a board without termination resistors where you can perform very simple simulations on is this Little Brain M2F4, which is a system-on module containing an STM32F4 microcontroller as well as some memory and various I/O. For this connection, for example, between the F4 microcontroller and this SDRAM at the top, I haven't used any termination resistors. If we'd like to simulate this, we can go to Tools, Signal Integrity, and then go to Model Assignment. Model assignment lets us, for example, assign models to passives, such as resistors and capacitors, but also maybe IBIS files to microcontrollers, SDRAM, and so on. But we can also choose standard logic families. So for example, for my STM32 microcontroller, I could choose standard logic families that are very similar to the actual characteristics of the device rather than importing IBIS. I'd like to make more detailed videos on this tool in the future, but for now, let's just choose standard logic families. Once we've assigned some models, I've assigned it to the microcontroller and the SDRAM. Let's look at, for example, one of these memory bus traces. For example, FMC-D3, which is a bidirectional data net between the microcontroller and SDRAM. This is an entire net here. What we'll do is assume that the microcontroller is the driver for now, so we're sending data to the SDRAM, which is our load or our receiver. The signal integrity tool has analyzed the design, and we can find all of the nets, as well as look at other data such as impedance, overshoot, and so on. So if I select FMC-D3, we can see the direction is from U2 to U4. Currently, we want to look at just no termination as it is currently on the PCB. To do that, I can click Reflection Waveform, and this is the waveform we get. The top waveform in red is from U2, so from the microcontroller. The waveform at the bottom is at the receiving end U4, the SDRAM. And we can immediately see, because of the impedance discontinuities, they aren't too large, but we can still see we have some ringing, overshoot, and undershoot on these transitions. So we'll go from a logic low to a logic high, and a logic high to a logic low. We can see this characteristic ringing, overshoot, undershoot due to these reflections because of these impedance mismatches. The simulation tool is really nice because without actually changing the schematic and the PCB, we can run simulations, for example, adding in series resistors, parallel resistors, and other termination schemes. For example, I can select parallel resistor to ground, and this will theoretically place a termination resistor at the load end, so at the SDRAM. I can perform sweeps as well, for example, from 50 to 200 ohms with the termination resistor, and then plot the waveform. We can see the waveforms here. Keep in mind, I've selected a very generic model, not an IBIS file for my SDRAM and for the microcontroller, meaning that actually the model I chose and the models available aren't strong enough to drive, for example, 50 ohms, and that's why you'll see these DC drops on the logic high. What we're interested, however, and for now, to take this with a pinch of salt, we're interested in the transition behavior. And this is just to show also that you need strong drivers to drive these low impedances with parallel termination. For example, if we select one of these waveforms, waveform with a termination resistor over 180 ohms, we can see we've already substantially decreased the ringing, overshoot, but we do have some undershoot still. With the termination resistor closest to my trace impedance, which is 50 ohms in this case, we can see there's quite a significant DC drop because this simplified model of the driver doesn't have the current requirements to drive this heavy load, this 50 ohms at DC. Therefore, we have this DC drop. We're interested in the transitions for now. So in the original waveform, we can see this ringing, overshoot, and undershoot. I can zoom in, for example, on this falling edge transition. We can see we have a couple hundred millivolts of overshoot, undershoot, and ringing. And with our termination resistor of 50 ohms, looking at that same falling edge, we can see this is very smooth and we have significantly less overshoot, undershoot, and pretty much eliminated all the ringing. And this is why we use parallel termination or termination in general. To give you a quick example where parallel termination might be used, we saw this PCB at the start of this video. This is this ZBRET, which is a actively educational development board, which is also used in my advanced digital hardware design course. We have an AMD Xilinx Zinc system on chip, various DDR3 low power memory, various peripherals such as gigabit Ethernet, USB high speed, and so on. Where I needed parallel termination, and where you generally do, is for DDR3, DDR4 interfaces. In this case, I've routed this as a flyby configuration, meaning I route data point to point between the modules and the controller, but address command and control signals I route from my host controller, which is the Zinc, to the first DDR memory module, to the final DDR3 memory module, and then I end this with parallel termination with these resistors scattered around the last device. This interface is very high speed, the trace lengths are above critical lengths, and therefore parallel termination is needed in this case, and we have very strong drivers in the memory controller, which is needed as the termination resistors are rather low value to match the trace impedances. From a schematic point of view, we have the address command and control signals, and these are internally terminated in the memory and the host controller, as these are point-to-point connections. But these blue traces are these address command and control signals, and these require parallel termination. This specific type of parallel termination is called VTT termination because we're actually tying these termination resistors to a specific voltage, which is actually a reference voltage at half the supply rail of the DDR3 memory bus. We have these single-ended termination resistors of about 55 ohms. We could use 50 ohms because 50 ohms is the characteristic impedance of my traces, of these single-ended traces. So remember, 50 ohms or above to minimize undershoot. So we can go, for example, 10% above to about 55 ohms. We can also see an example of differential termination impedance for this clock pair. This doesn't need to be tied to any voltage. The termination resistor sits between the positive and negative part of this differential pair, matching the characteristic impedance plus about 10%. So 100 ohms to 110 ohms for this resistor. These resistors are placed at the end of the chain as we saw, and the single end ones are tied to this termination voltage, this VTT voltage, and we need a sufficient amount of decoupling in the case of this DDR memory. In terms of layout and routing, go to 2D view, then we start the host controller, these blue traces. We route over to our first memory module, we route over to our second memory module, and then finally, as short traces as we can, again trying to keep them as lumped elements, from the last memory IC over to our termination resistors scattered close to the device and placed sensibly. In this way, despite a fast rise and fall times and the rather lengthy traces, we can minimize the reflections in this system. Thank you very much for watching this video. I hope it was useful and I hope it gave you an introduction and the basics when it comes to termination and parallel termination. In future videos, we'll look at other termination schemes, such as series termination, which is incredibly useful as well. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any of the latest videos. Thank you, and I hope to see you in the next one. Bye-bye.